To day 3 of limits. Okay, today we are proving continuity. So for a graph to be continuous, we know that that means that there are no breaks or holes or gaps on the function. Okay, so you can see here this first graph on the right that we can graph that and trace it without lifting up our pencil. So that is what makes it continuous. Okay, so graphs that are the opposite of that are called discontinuous. So they have breaks and jumps and holes in our graph where we cannot trace the entire thing without picking up our pencil. So we have actually talked about these different types of discontinuity before. Okay, we can review them and talk about what they mean in terms of limits now. All right, so we have seen infinite discontinuity. And we know that that happens when there is a vertical asymptote in our graph. Okay, so in terms of a limit, what is that going to mean? Okay, so think about that for a second. And a jump discontinuity comes from a piecewise function. So we have 1/2 of the graph coming from one equation and another piece coming from a second equation. And then removable discontinuity is from a hole. So remember, that is one specific value that we remove from the graph. Okay, infinite and jump are called non-removable. That's just kind of an extra little piece of information for you. So in terms of a limit, okay, so for the infinite discontinuity, the limit from the left would go to negative infinity. All right, if we're just talking about this specific graph, it's obviously different for each function. And the limit from the right would approach positive infinity. So that is not going to exist because the left and the right are approaching two different values. So the two-sided does not have an answer. Similar situation for the jump. Okay, from the left you could be approaching one y value, and from the right you are approaching a second. So instead of approaching infinity, they're coming to specific y values. However, the overall outcome is the same, that the limit does not exist. Now with removable, we know that the left and the right side of the graph is getting closer and closer to the same value, which is the whole. But we can't actually evaluate the function there because that's undefined. So the limit can equal the whole and have an answer when it's removable, but evaluating the function is undefined because we can't plug that x into our equation. So there are 3 steps that we have to use. We're creating a formal proof here in order to show or, not show that a function is continuous. Okay, so step 1 is going to show that f of x is defined at the value that you're given at c. So that means that you're going to calculate f of c. So you're going to use direct substitution there and plug it in. Step 2, you are showing that the limit as x approaches that same c value exists and has an answer. Step 3 is now a conclusion, and you're showing that f of c has the same answer as the limit as x approaches c. So that is the only way that a function can be continuous. If it is evaluated at a value and if it has a limit at that value that are both the same answer. Okay, it sounds a little confusing, but it actually is a very easy process. You just want to make sure that you hit all 3 of these steps. Okay, remember, we're creating a formal proof. So we're determining if f of x is continuous at x equals 2, and it says use the test for continuity. So this is our 3-step process. All right, so step 1, and you can set it up exactly as I'm doing, says evaluate f of 2. So that means we're going to plug 2 into our equation. Okay, so when I evaluate this, I get 1. Okay, so f of 2 equals 1. Great. Okay, you can evaluate the limit graphically, or you can evaluate algebraically. You can use either method. So I'm going to choose algebraically for this one. Okay, so I have this equals 1. All right, so the limit, okay, and I'm stating everything very formally because that is what you do in a proof. All right, so now step 3, I need to show that step 1 and step 2 were equivalent. So f of 2 equals the limit okay, and they equal 1. So f of x is continuous at x equals 2. Okay, you do need to write that conclusion. Okay, in similar terms, if not the exact way that I wrote that. Okay, but see, it's a very easy process. So this one worked out well for us because it was continuous. That might not always happen. Okay, so finding continuity for a piecewise function. All right, when we evaluate the function at the x value that's given, so at -3, we're going to use the piece of function where it's actually equal to -3. So for step number 1, I'm going to be using 2 minus x because that is where the piecewise is actually equal. Okay, so the function is defined there. Now step 2, we're finding the limit. And remember, for piecewise functions, one of those equations is the limit from the left, and the other one is the limit from the right. So we actually have to calculate both of those algebraically. So I see that the limit from the left and the limit from the right do not approach the same value. So that means that the limit does not exist. Well, what is my conclusion then? So obviously, f of -3 does not equal the limit as x approaches -3. So that means f of x is not continuous there. But now I have to state the discontinuity. So what is actually happening there? Is it a vertical asymptote? So it's infinite? Is it jump? Is it removable? This is a piecewise function, okay? And I know if one side is at the y value of 5 and the other side is at the y value of -11, I would need a line segment to fill in that space to make the function continuous. So this is a jump discontinuity. Okay, and you want to make sure that you state what kind of discontinuity it is, in addition to the conclusion that it is not continuous. All right, let's see what situation this one brings us. So step number 1 is always to evaluate. So f of 1 equals so f of x is not defined at 1 because I get 1 over 0 when I try and evaluate. Okay, remember when we're finding the limit and it's undefined algebraically, that means the limit does not exist. So what is my conclusion here? Well, my conclusion is that f of 1 is not even defined on the function. And the limit does not exist. So obviously they're not equal, and this cannot be continuous. So then what is actually happening here? It can't be jump because it's not piecewise, and I didn't cancel anything out, so it's not removable because I didn't create a hole. However, the value that they're asking me to look at happens to be the vertical asymptote of the function. So this is an infinite discontinuity. And we have one more. All right, so you still want to factor and simplify as your first step, okay? Even when we're doing continuity. Okay, so I have a simplified function. However, when I evaluate, and I do step number 1, I want to use the original function. Okay, so when I evaluate at 3, okay, I want to see that this is undefined. Because remember, the limit can equal the whole, but evaluating the function at the whole is undefined. And we can only get that if we use the unsimplified version. Okay, when you find the limit algebraically, we can use the simplified function. Okay, so this is also, when I evaluate algebraically, I get undefined, but for a limit, that means it does not exist. Okay, so step 3, f of 3 equals undefined. And the limit does not exist. So we certainly cannot be continuous there. So again, what is happening at x equals 3? So even though we created a hole in the function, that's not the x value that we're looking at. We're looking at the x value where there is a vertical asymptote. So this is an infinite discontinuity again. All right, but I wanted to show you this example so that you see in step 1 and step 2 that you use different versions of the equation. Okay, so step 1 you use the original, and step 2 you're going to use the simplified. All right, so we're going to do a lot more work with this when we are in class, but please make sure you have down your 3 steps for the proving process. Okay, and you've completed these 4 examples. All right, if you have any questions, write those down as well, and we will make sure that we get to them. Thank you so much for watching, guys. I will see you next time.